selected. And so this is where we can use a technique called classification. And we're seeing an example where we've got four groups of subjects on the left that were sort of partially separated by PCA. On the right, we're using a more powerful technique called partial least squares discriminant analysis, or PLSDA, to pull apart or separate things even further. So this dives into the area of clustering versus classification. Clustering can be improved if the clusters are labeled or pre-identified. That's essentially adding additional information, saying, well, these ones are the sick ones and these ones are the healthy ones. By adding that additional information, we can carry out essentially a supervised separation. So supervised separation is called classification. And as I said before, classification is fundamentally different than clustering. Clustering is unsupervised, classification is supervised. Classification can be predictive, where clustering is not intended to be predictive. It's just to facilitate classification. Clustering is done by PCA. Classification is done by partial least squares discriminant analysis. And just to sort of contrast the differences of what we get, on the left side are examples of PCA clusters done on metabolomics data. And the top left corner, we can see that basically there's no separation. We can then apply PLSDA, and we can get a partial separation. The reds do start separating from the greens. Now, this may be a situation where we're over-interpreting the data. And I'll get into this concept of over-interpretation, over-training. On the lower example, we've got four classes. The PCA sort of separates them, but by applying PLSDA, we can see even greater separation and more distinct groups. And this is done because we have essentially labeled the data and said, these are the groups that exist. Add this information to your clustering/separation process. So this is just a comparison between PCA and PLSDA. PLSDA is partially squares discriminant analysis. PLSDA uses labeled data. It's a classification technique. PLSDA enhances the separation between groups by rotating the PCA components such that maximum separation among the labeled classes is obtained. So PLSDA not only performs a clustering process, it also learns and can be used as a predictor. So it's a categorical predictor. So PLSDA learns through large multivariate data sets. Once the PLSDA model has learned on a training test, then it can be used on new data as test sets. PLSDA, which was developed in the 50s and 60s, is in essence sort of a precursor to machine learning to perform classification. PLSDA is more of a statistical method, whereas machine learning has elements of neural nets and other techniques. There are lots of other classification techniques like logistic regression that can also be used to separate categories or classes. When you are separating on the basis of categories or classes, binary classes, yes, no, sick, healthy, control cases, you have to use different measures. You don't use correlation coefficients. You use something called sensitivity and specificity. That measure of sensitivity and specificity is sometimes called or part of a confusion matrix. If you've got two categories, you can have things that are predicted to be true and or positive and actually shown to be positive. You can have things that are actually positive but predicted to be negative. You can have things that are predicted to be positive but actually negative, and you can have things that are both actually negative and predicted to be negative, and those can be called true negatives. So we have within categorical groups true negatives, true positives, false negatives. We can measure things in terms of sensitivity and specificity. Another way of depicting these things is to look at sort of data as if it was in sequence or in perhaps sequences like genes or proteins. So if we have genetic coding regions and non-genetic coding or non-coding regions, we can identify the same thing between actual and predicted. So if we have a gene predictor that is marked in red and actual genes marked in blue, we can see where the prediction overlaps. Those are true positives with the actual gene. We can see where it misses or overpredicts. Those are false positive. We can see that it predicts the non-coding regions. Those are true negatives. And then we can also see where it underpredicts, and those are false negatives. Sensitivity and specificity actually have equations that are associated with them. Sensitivity is a measure of sort of the true positive rate. Specificity is a measure of the true negative rate. Precision is a little different than either of them. It's often confusing to know what is sensitivity if you haven't got the formulas remembered. But sensitivity measures the true positive rate. So N corresponds to P. And specificity measures the true negative rate. P corresponds to N. In sensitivity, the high false negative means a low sensitivity. In specificity, a high false positive means a low specificity. Screening tests need to have high sensitivity. So N is a letter in screening, and N is in sensitivity. Surgical decision tests need high specificity. So the C in specificity is there in decision and surgical. So those are some mnemonics just so you can help distinguish when and how and why sensitivity or specificity is preferred in certain types of tests. There's also a tendency with regard to sensitivity and specificity in different fields. So information retrieval studies report precision and recall, whereas in bioinformatics, genomics, proteomics, we tend to report specificity and sensitivity. Really, in any kind of assessment, you want to maximize both sensitivity and specificity. If something is both sensitive and specific, it's better than something that is just specific or just sensitive. And one way of essentially capturing the performance of sensitivity specificity together is through something called a receiver operating characteristic curve, or ROC curve. This is something that was developed in the 1940s by radar engineers in the UK who were trying to identify German bombers as they were flying over. They were using radar to determine whether the bombers were actually German or whether the bombers were actually flocks of geese, because back then radar wasn't very precise. So they were tracking on the performance and whether they had hits, misses, false alarms, or correct rejections. And this is some data collected from that, where you had the percent of German planes detected, which is a measurement of sensitivity, percent of geese flocks correctly identified, and then the incorrect identifications. And if you plot out the sensitivity and specificity, you get a curve that's shown on the bottom right, where it sort of looks like a log curve or a logistic curve, things climbing up and maxing out to 1 or 100. So a good ROC curve, one that's a test or a predictor that's highly sensitive and specific, should look like a logarithmic curve. A poor ROC curve, one that's just a random guess, would just be a straight line with a slope of 1. The area under the curve, or AROC, is a good measure of the quality of some predictor or biomarker or discrimination tool. As a rule, if AUCs are greater than 0.75, it's pretty good. AUCs of 0.5 is totally random, and an AUC of 1 is perfect. So the area under the curve is sometimes called a C statistic. So we can calculate sensitivity, specificity, areas in the curve if we look at something where we have a predictor which is able to separate these two populations in the format that's illustrated here. So we've got what we'll call negatives. These might be negative patients, they might be cases in orange, and then on blue, the right, are called positives. And those could be controls. So we can distinguish the ones that are the negatives. There's the ones where there's no overlap, or the true negatives. Where there's an overlap with orange and blue, those are the false negatives. In the case of the positive patients, the area that's all blue is called true positive, and the overlap with orange is called false positive. So if that's the way that our predictor has been able to separate these two clusters, so let's say it's a PLSDA predictor, then we can start calculating the ROC curve performance for that predictor. So here's the two curves against, the cases, positives versus the negatives. And what we can do is we can draw cut points along this distribution. So we've colored the lines. There's 8 different cut points, and we've started on the right and moved our way to the left. So it's green, purple, more green, yellow, orange, red, brown. And where we've done or we've cut these things, then what we can do is calculate the number of true positives and the true negatives, which is sort of the number under the blue line and the number under the red line. So we can then plot those numbers out, and they show up on this curve. So we can see at the very top of the curve is where the brown line is. Just a little bit to the left of the plot is the red line. There's a red dot, and there's an orange dot, and we go all the way down to the far left corner where we can see the lime green near the bottom. And this way we've been able to plot out specificity and sensitivity, true positives, false positives, and put them onto a curve. We can then draw a line through those 8 points, and that's now officially the ROC curve. And we can choose certain areas which will give us either better sensitivity or better specificity, or the maximum of both sensitivity and specificity. So in this case, on this side, we have relatively low sensitivity and relatively high specificity. In this region, we have relatively high sensitivity and relatively modest specificity. And at the inflection point, we've kind of got the best of both worlds. Pretty good sensitivity and pretty good specificity. The area under the ROC curve is a more useful statistic, and typically when you're trying to come up with a predictor or a model that can separate between two categories, you measure it through this AUC. So good predictors, good separators, good models will typically have AUCs of 90%. Moderate ones will have 70%. Perfect ones will have 100%. Random ones will have a value of 50%. So again, just to remind people, you can have either numerical predictors, which are shown on the right, and we have to evaluate those based on correlation coefficients, or you can have categorical predictors, and those have to be evaluated using area under the curve. PLSDA is a very good technique for doing categorical prediction. Linear regression and parametric equations are good for doing numerical predictions. Now, regardless of whether you are doing numerical or categorical prediction, you still have to do testing and validation. So remember, we talked about training and testing sets for the numerical correlation predictions. Same thing has to be done if you've got a categorical predictor like PLSDA. So they are class predictors. They need to be tested. They need to be validated. In principle, you can have holdout sets and training sets, test sets and others. But because those are a little more difficult to build for categorical predictions, especially for PLSDA, there's a tendency to do different or approach it differently. So in the case of PLSDA, there's R squared and Q squared assessments, and there's also permutation testing. So PLSDA, you can calculate the correlation index, or coefficient of determination. And just like the Pearson correlation coefficient, it ranges from, 0 to 1, or at least the square of that. It essentially is a measure of the quality of the fit. Q squared is different than R squared. It's sort of the predicted variation, or it's a measure of the quality of prediction. However, Q squared and R squared almost always are the same. They track very closely. Overall, R squared is a quantitative measure. It's a measure of how well the PLSDA model reproduces the data in the data set. So in essence, you can think of it as a correlation. Just like correlation values, Pearson correlation values, if they're around 0.2 or 0.3, those are terrible. If they're about 0.7, 0.8, they're very good. The Q squared is basically a measure of the cross-validation performance. So n-fold, three-fold, two-fold cross-validation, and it makes sure that the data holds up to the cross-validation. As a rule, if the Q squared is greater than 0.5, it's a good, well cross-validated model. If it's above 0.9, it's exceptional. This is an example where people have taken a PLSDA model and used different components. So remember, you can use just one dimension, or two dimensions, or three dimensions, or four dimensions, one principal component, two principal components, three principal components. And you can see that by about two principal components, or two PLS components, the model passes the threshold for being satisfactory. Everything's above 0.5. As you add a few more components, this is equivalent to adding more metabolites to the model, the model performance improves. And it maxes out around 4 or 5 components, meaning it could be 4 or 5 metabolites or combinations of metabolites. You can also see how R squared and Q squared are basically the same throughout the entire plot. So that's one way of assessing a performance. Another